Hi, and welcome to the last lecture of this class. And it is chapter 12, and it's all about theory. So, as always, please, take it with a grain of salt, just like last chapter. There's a lot of theoretical. I took out a lot of the math stuff going on. You can go ahead and read that in the book if you would like. But it's not really where this is coming from. This is just for informational purposes so that you can kind of gain an understanding as to, what the theory behind some of this computational type items are. So let's go ahead and get started. In the book, we're covering the first 5 sections of this chapter 12. We're not going to talk about the public key cryptography. If you were in my class earlier this summer, we did talk about that just a little bit, but we're not going to talk about it in this class at least. So a little bit more going on than what I had wanted to discuss with y'all. So let's go ahead and get started in talking about functions. So functions and their computation. A function is going to be a correspondence between a collection of possible inputs and a collection of possible outputs, so that each input has a single output. This is the same definition that we learned back in math in middle school. Okay, a function is a one-to-one. If you think of an XY graph, we learned, as you move from left to right, as long as it only crosses one point on that line, it is a function. It's the same idea behind it. Okay, so this graph this figure right here is a function which is going to convert from yards into meters. So as you can see, each yard has a corresponding amount in meters. So you can't have that 1 yard equals 2 different types of output for meters. So that's what we're talking about when we're talking about function. Now, computation in functions. So computing a function is going to determine the output value associated with a given input, given some type of equation or a set of input values. So this is basically what we're saying is we are calculating what that corresponding output is with a given input and then some logic in there. If it is non-computable, then a non-computable function is a function that cannot be computed by any algorithm. So if it's an arbitrary random number, or if just for some reason it can't be computed by algorithm, then we call that non-computable. Now, Turing machines. A Turing machine is a theoretical computing machine started by Alan Turing in 1936. It is used as a tool for studying the power of algorithmic processes. So what you're going to do is you're going to have some inputs, it's going to have actions, and it's going to have steps, and it's going to record that, and it's going to produce an output. So the operation of the Turing machine is that input, there are inputs at each step, the input is the state and then the value at the current position of where it is on the tape or the hard drive or the CD, wherever our storage is. Then there are actions at each and every step. It's going to write a value at the current position, it is going to move the head, and then it is going to change the state. So when we're talking about, I think the easiest way to picture this would be like an old-fashioned record player or a CD, which would act very similar to a record player. And so you can think about that head moving along the radius of the CD or the record. And so that is what we're talking about at the tape position. That tape position would be the position of where that head is in relation to the rest of the data on the disk. And then move the read-write head. What we're talking about is moving the like the record player needle in and out and moving it around. So that's changing the state. Now, the next slide. So this is a Turing machine for incrementing a value. So we remember each step has a current state and a new state, right, with some process in between. So we start at the start position. The cell has nothing in it. We don't want to write anything to it. We want to move to the left, and then we're going to do an add. Okay, so the add comes back. Okay, so you can see how it's kind of, you're good. The current cell has a 0. You're going to write a 1 to it. You move back to the right. Okay. The new state to enter is a return. So we're going to go back to where we started from, so that's going to go back to an add. So this is just kind of showing it's going step by step by step how that the computer components are actually moving on the hard drive. This is how it would measure efficiency. Now, the Church-Turing thesis, which is the next, taking it to the next level, is that functions that are computable, remember computable means we can calculate an output given some inputs in the process, by a Turing machine are exactly the functions that can be computed by any algorithmic mean. So if you can do your function as a step-by-step process, doing each step in baby steps, then it can be done with an algorithm, which kind of makes sense because an algorithm goes step by step, right? And you have to tell it each baby step before it can move on to the next. Next, we're going to talk about universal programming languages, and this is any language where you can find a solution to any computable function. Now remember, we're talking about those computable, so they do have a solution. So the most popular programming languages, that are out there are the bare bones languages, the ones that don't have all the bells and whistles, very easy to learn, very easy to understand, kind of more of like a pseudocode type looking language. So bare bones is a simple yet universal language. You have basic steps, and these kind of go back to those steps that we talked about in class 1 or 2, right? With the those addresses. So you can clear, you can increment, you can decrement, you can do a while loop, but you can see there it's very, very basic, very minimal. It's just going to, do one step or one thing at a time, and it just goes sequentially through the process. Now, a non-computable function, remember, these are the ones that can't stop, basically. So the problem that you have with them is getting them to stop, okay? They will just go on for an infinite amount of time because there is no actual solution. So given the encoded version of any program, it will return a 1 if it is self-terminating, or a 0 if the program is not. So it can actually communicate back with the operating system to say whether it terminated properly, which is a self-termination, or if it did not terminate it at all, and it can be a 0, which would be an error, some kind of error assignment. So this right here could be a testing of a program for self-termination. So here we've got while x is not 0. So what we're saying here is x is going to be what is returned back from this algorithm of all the colors, okay? So it's going to be one long bit pattern using ASCII over here. You're going to go through and find every single letter. If it terminates somewhere in the middle there, it's going to return a 0. So then it's going to kick back out to that while, and that's what's going to make it stop. So you can have built-in, steps in there to see if it actually will stop or won't stop. And if it's not going to stop, you can make it stop. Now, proving the unsolvability of the halting program. So this right here is going through, and first you propose that you have an algorithm, and then you can modify it by adding that while not 0 structure. Now, if it were to self-terminate, it will actually complete the algorithm as written. However, we're coming down to the bottom left now. If the new program were to hang up, have an issue, have an error message, it's going to get stuck into that loop, and it'll be kicked out of that loop, right? So if it has a function, it will be able to stop itself. So again, you can write it into your code to make it stop. The complexity of problems. So we can make problems as complex as we would like or as simple as we would like. So time complexity is the number of instructions required to do a process. So unless we say otherwise, we're talking about time complexity when we just use the word complexity. So here, there's some math and stuff in there, but basically what it's saying is the more steps you have, it's going to take more time in a nutshell. So if you have 8 steps, it's going to take, somehow 8 increments of the execution added into that time component. Okay, don't get caught up in the maths and the thetas and the O's and the functions and all that stuff. Just know time complexity is going to be the number of instructions that we need to execute in order to complete the process. Here we have a hierarchy of problems generated by the merge sort. So here we've got a sort list of n names. When we look at that, usually for a hierarchy, we take, okay, are we in the first half or the second half? And then from the first half, we say, okay, is it in the first quarter? We basically just keep dividing it in half, right? So what this is going to do is it's going to basically drill down until it finds the value that it needs. So it's going to keep dividing it by 2 until you find the acceptable value. So NP problems. So class P problems are all class where you have a polynomial as a function. If you remember in math, polynomial is just an equation that has a value. Now an NP problem now is basically the opposite of that, okay? So they call it a non-deterministic algorithm in polynomial time. So a non-deterministic algorithm, big old words. It's just an algorithm whose steps may not be unique and completely determined prior to starting. So you kind of sort of know, but you're not terribly sure. How's that? So whether the P case or the NP case is bigger with its issues, it's currently unknown. They each have their own set of problems that occur whether you're using a P or an NP. So it's not really dependent on whether you know that value or not. And before I blow your mind, last but not least, the last slide of the evening, or the lecture. So I guess if it's daytime for you. Here is a graphic summation of the problem classification. So as you can see here, you've got NP problems, and you've got P problems in your solvable realm, and in your unsolvable realm, we're just not even going to talk about those. But within that solvable problems, we can say we've got polynomial problems and then non-polynomial problems. And the ratio of what is what in the whole realm of solvable problems, that's an unknown. But we kind of think of it as a 50-50, okay? Kind of like what's shown here. So that is really not limited to what type of problem it is when you're looking at the theory behind it. Now, again, please, this is a short lecture, great one for the last lecture. It's very, very intensive and theory-based. Just let it wash over you. I didn't put any questions in a knowledge test or knowledge check for you guys for this. There's going to be a few on the midterm, maybe like 1 or 2, not a whole lot. So please don't stress over this lecture. So as always, I'm here for you if you have any questions, comments, or concerns. It's been a pleasure having all of you in my class, and I hope to see you all soon. Bye.